All right. In this video, I'm going to show you how to make this image of Messier 16, the Eagle Nebula. And I'm really happy with how this one turned out. This one turned out really nice. And one of the reasons why it turned out so nice is a bunch of data, a bunch of observations went into it. Now, normally, students or small groups of students or their instructors, as part of the multi-wavelength universe curriculum, won't have this many observations. They're working with smaller data sets. And the reason why is telescope time is expensive. We can only give out so much per student. So how did we get this data set? Well, each year I run a summer program at Green Bank Observatory, which is a radio observatory, and I bring 18 to 21 undergrad students. And mostly we do radio astronomy projects, but we also do a few optical projects. And since these tools that we've been building into Afterglow are pretty new, we decided to give them a whole bunch of telescope time and see what they would do with it and use the tools and see how it goes. So we gave them a bunch of telescope time, and we gave it to them. We do sell telescope time to institutions around the world for research and education. It's partially how we pay our bills and keep Skynet running. Now, again, for these students, we just gave them the time. We didn't sell it to them, but the amount of time we gave them, had we sold it, would be worth about $2,000. So this was a splurge and a great opportunity for them. And they understood this and they picked their targets carefully. And a lot of them observed the Eagle Nebula. They observed, I don't know, maybe about a dozen different things, but a lot of them chose the Eagle Nebula. So we got a lot of data on the Eagle Nebula. And some of that data, maybe about half of the data came back during the 1 week program, and they used it to make astrophotos, and the rest kept trickling in afterwards. So about a week after the program, I went back and saw how much data they did collect. And they collected about 5 hours worth of data on the Eagle Nebula. And so 5 hours on this telescope, which is the Prompt 6 telescope at Cerro Inter-American Observatory, our best site in the Skynet network, it's worth about $500. So again, this is a splurge. Okay, so I grabbed all their data and put it together. So first off, credit where credit is due. These are not my observations. The observations that went into this image belong to the following students. I'll just read off their names: Megan Greensmith, Finn James, Craig Kalkworth, Nick Cones, Alex Pracken, and Brady Smith. I should say 2 of them, Finn and Nick, have already graduated. They were young educators on this program. So students and former students. Okay. And let's break it down by filter. They got 63 minutes in the B band, 54 in the V band, 54 in the R band, 36 minutes in the luminance filter, and a whopping 71 minutes in the H alpha filter. So a really nice data set, particularly when you pull it all together. So what I'm going to do now is get this out of the way and show you how to make that. I did this a few days ago, so we're going to see if I can remember all the steps that I did and see if I come up with the exact same image. Let's start assuming you have your stacks. I'll shoot another video on how to produce stacks, but basically you have all your individual images. And in their individual images, they varied in duration, but most were 30, 60, some were 80 seconds. Anyway, stacks is the process of taking all of your images in a single filter, putting them together, in such a way that you get rid of camera defects and you increase your signal to noise. Okay, so we've got some pretty good looking stacks. This is the B filter. And you see these stars here are really bright. This is the whole engine of this image. These are the new stars. And you have stars of all the colors in here, but the most luminous ones, the brightest ones, are the blue ones. And so they show up really strongly in the B filter. V got a little bit dimmer and some other stars popped in. And that will be our green channel. Here's the R filter. This would be our red image. Again, these are getting a little bit dimmer because they're blue stars, at least the bright ones. And we're starting to pick up red stars throughout the nebula. As I'll talk about, there's a lot of dust along this line of sight. And dust obscures blue light, making stars red. And so there's a whole bunch of faint red stars here. A lot of it due to dust. But also, we see this kind of band of color, not band of color, band of brightness. If we go back to the V image and the B image, we don't see that. But here in the R image, you see this band of brightness. And this is from H alpha, the narrowband emission line, hydrogen alpha. And again, I said these stars here are driving everything. They're young stars, hot stars, luminous stars. They're heating the gas around it. And that gas is expanding and pushing up against the cloud boundaries, pushing around little nodules, creating these pillars and spires that point back towards the hot blue stars. But up against the cloud boundary, there, light from these stars, it's exciting hydrogen. And the hydrogen, then the electrons de-excite, giving you emission lines. And anything coming back down to the first excited state and from higher up gives you Balmer emission. And the first 4 Balmer lines are in the visible part of the spectrum. And the strongest one is H alpha. And then you have H beta, H gamma, H delta. H alpha is the strongest and it's in the red. And so that's what we're seeing here. That's why you have that band of color. Go to the luminance filter. It looks almost the same as the R filter. It's a broader filter. You're taking in more light, though they got a little bit less data here. So it looks very similar to the R band. And then finally, we have H alpha. And this is a narrowband filter right around that hydrogen emission line. And so it's picking up all that Balmer emission. It's also picking up stars that cross this band as well. Okay. And these are really good looking stacks. I'm not seeing many defects or anything. All right. So let's start putting these together. I did this a few nights ago, so hopefully I can remember all the steps and come up with the same image. First step is to select all of them and then group them. Is you're taking these individual FITS files and combining them into a single multi-layer FITS file. It's done that. We have our color layers here. Let's take the luminance layer and put it above the color layers. There we go. And let's take the H alpha layer and put that above the luminance. This is kind of the order that we're going to do it. We'll start with the colors, and then the luminance, and then the H alpha. Now, if we click on the top level, it shows us the combination of all of those. And they're all just colored gray and thrown together using the screen blend mode by default. And it makes a rather interesting, wild picture, but it's not what we're going for. We're going for color combination. So let's start with the color layers. So let's turn off the H alpha and turn off the luminance. Let's color the R band right click, color the R band red, the V band green, and the B band blue. Okay, now the initial combination it says manual, but since we haven't done anything yet, it actually sets it up with the percentile combination, then puts it back into manual mode for frame-by-frame editing. Let's go to percentile, make sure we know what this is. And you can see it's using a linear stretch mode, which is not the best, but we'll start with that. And what it's doing is in each layer, each color layer, it's going, you can see here 10, it's going 10% of the way up from the bottom of the histogram. So from the bottom of the image, the faint end of the image, it's going up 10% of the pixels and setting that as the background layer in that particular background level in that particular layer. And then it's coming in 1% of the way from the top of the histogram, from the brightest pixels. It's finding the brightest 1% of pixels and then setting that as the top level for each individual level separately. And that, that's not natural color. That's just some algorithm. And it's actually pretty close to natural color, pretty close to how the human eye would see this, but not exactly. But it's easy to calculate, so Afterglow starts with that. If we want to do natural color as well as we possibly can, we'll go into the histogram fitting mode. Let me hit default preset. Once you change modes and display settings, you always have to hit default preset. And here the image is very red, simply because the red channel, the colors of the histogram don't correspond to the colors of the channel. This one out here, the one that's colored green, is actually the red channel. And just the values are higher in the red channel, everywhere in the image. And so you can see that because the histogram's to the right. And this is actually the green channel, and this is the blue channel. And it could be different exposure lengths, different throughputs. There's a wide variety of reasons why these may differ. They're not calibrated yet. We're about to calibrate them, set the levels. These are just what came off the chip. And the numbers were higher in the red channel, so it's a very red image. Now, let's calibrate it. For that, we're going to go to Photometric Color Calibration. And the blue channel will be B, the green channel will be V, the red channel will be R. And there's some numbers in here because I was playing with it before I started shooting this video. But you would then press this button. It's probably going to come up with the same numbers since I was working on this image. And what it's doing is in each of those frames, it's extracting the sources across the image, measuring the brightness within Afterglow, and then matching each of those stars up with catalog stars and their measured brightnesses, and looking at the difference there to calibrate that particular frame with respect to the others. And that's what these 0 points are. The reference layer doesn't really matter. It's going to shift these histograms, and we're just picking which one will be the reference. The others will shift to it. I'll just pick the blue one, this one here. And then finally, the white balance. And if you're observing in the B, V, and R filters, those approximate the human eye pretty well. The blue, green, and red response of the human eye. It does a pretty decent job. And the human eye sees black bodies, thermal distributions, peaking in our blue filter as white. That's what we see as white as humans. Thermal distributions that peak in our blue filter, which is like the B band, we see those as white. And so we're going to use that white balance there. And extinction, will come back to it. Neutralize background, that should be checked by default. So let's calibrate the colors. And again, you're going to have to hit the default. Okay. So this is calibrated, and this is what you would see. If the eyes were more powerful, which they could be made more powerful by looking through a telescope. A telescope can collect a lot of light and funnel it into the eye faster than the eye would by itself. And if you get enough light going into the human eye fast enough, you can register colors. And these are the colors that you would see, or at least pretty close to it. Lots of reds, as we were talking about. And, before I was describing these stars as blue, but they don't look very blue. And it's because of all this dust. There's a tremendous amount of dust between us and the source. And dust scatters out blue light preferentially. This is a really challenging target because of how much dust there is. And so, if you Google this online and skip over the ones done by Hubble Space Telescope, which are in something called the Hubble palette and, much greater resolution, a lot of amateur photos of the Eagle Nebula look like this. But these are not the true colors of the stars. You can look at them and those don't look like stellar colors. They're dust extinguished stellar colors. So the way an astrophotographer would deal with this, suppose you wanted to restore the natural colors of the stars, as if you were there, not looking through all the dust between us and there. What they would do is they would play with the white balance until they get natural looking colors. But that's not the approach that we take in this course and in these video tutorials. We're trying to take a more physical approach. Changing the white balance is not physical. It's changing the definition of white. The human eye, we're using filters that match the human eye, so we should use the white balance that matches the human eye. The reason these stars are not as blue as they should be is because of dust. So let's just correct for the dust. We understand how dust scatters light at each wavelength. And so there are these things called dust extinction curves that describe this. You just have to specify how much more dust scattering you have in the B band than the V band. And then the curves do the rest. And that's what this is right here. Let's go back to photometric color calibration. EB minus V is how much more reddening do you have in the B band than the V band in magnitudes. And you can look this up for different sources. WebDA is good. Messier 16, it has an NGC number of 6611. And so you look that one up and the reddening is 0.782. That's how much more reddening you have in the B band than the V band. 782. And that's a lot. It's almost a magnitude just from one filter to the next. 0.782. So we're going to calibrate that. Okay, and then you want to hit default again. Okay, and so this is looking a lot better. These are looking like thermal blues, the blues that you get from a thermal distribution. And we have other colors in here as well. So these are the colors you would see if you were there. Move through all that dust, get there, so the dust is behind you, and look at this. These are the colors that you would see. Okay, so we've achieved natural color, but the brightness and contrast settings are non-ideal. If we look at this, there's a lot of detail, wonderful details in the faint end of the image, the nebulosity. There's a lot of structure in the nebula, but right now it's too faint and we can't see it or can barely see it. So the faint end of the image we want to boost. And then the bright end of the image, the bright stars, they're all blown out. Even if you come down to these intermediate brightness stars, once you move in here, it's just a uniform field of color, and we're missing out on all the structure. So the faint end's too faint, the bright end is too bright. And so you can adjust this by adjusting the brightness and contrast. And you can do it in the color layer, in the color composite. But we're going to use a luminance layer. The idea with the luminance layer is you observe this field in a broader filter, bring in more light, so you have greater signal to noise. And if you use a luminance layer, the intensities come from that luminance layer where you have better signal to noise, but the colors come from what we just did. So there's no need to mess with the brightness and contrast settings. It doesn't change the colors, and that's all we're actually taking from the composite that we've done so far. Okay, so for the luminance layer, what you want to do is we're going to leave histogram fitting, go to manual mode, and double click on the composite layer to lock it in, and then double click on the luminance layer And we're gonna split right. Fit to zoom. And let's turn this layer on. And we're gonna set its blend mode to luminosity. And it just looks white right now because the background level and saturation level aren't set. And it's set based on the previous images and not based on this one. So what have we done here? We split it so we can see both the composite, the luminance layer. Over here, the luminance layer, we keep the color gray. We set the blend mode to luminosity. And now we can click on the luminance layer and we can hit the default here. Okay. So the background and saturation levels have been reset to the range for the luminance layer. And again, we're taking the intensities from here, combining them with the colors from underneath to make this composite. Now it looks about the same because we're still in this linear stretch mode where the faint is too faint and the bright is too bright. So we're going to switch to midtone. And these other ones, they're all simple modes like linear, log, square root, hyperbolic, arc sine. If you click on any of these other ones, click on hyperbolic arc sine just to demonstrate. It gives more, it boosts the faint end, but it blows out the bright end even worse. And it's true for any of these. Here's square root. Here's logarithmic. They're all really good for looking at the faint end, but they just blow out the rest of the image. So those are simple modes. This one is a little bit more advanced, midtone. It comes with an extra parameter. You go here, going to hit the default preset. It comes with an extra parameter. So you have a background level, the saturation level's here. I like to keep it in percentile mode, just because I'm used to thinking about percentiles. And then you have this extra, it's called a control point in between that we can slide around. And because of that extra degree of freedom, we can have a lot of detail at both the faint end and the bright end simultaneously. Now the saturation level, the default comes up as 99.999. It's almost the very top of the image. It's being set to white here. And the background level, for nebular regions, I have different advice for different types of regions. For nebular regions, I often like to lower this down to 0. You have a lot of, I'm just going to check my notes. Yep, that's what I did before. You just have so much detail down here near the bottom of the image. There's structure everywhere. I don't want to miss out on any of that. And so I go to 0 or 0.001, something like that. 0 looks fine to me. And then we'll just adjust the mid-tone level until we're happy with the brightness of the image. Let's go up. Let's try 99. Okay, that's too faint. Go down to 95. That's a little too bright. That's a little washed out. The default was 97.5. Oops. You got to type it fast. 97.5. I don't know, that's a little bright. Let's try 98. Yeah, 99. Too faint, 98. You could play with it. I'm going to go with that. What I'm looking at is kind of the structure down here when it comes out. At 99, I can't see it very well. 98, I can. 97. No, it's starting to wash out this region over here. And it'll be different for every image. If you collect your own data, you have to find your own level that works with that particular data set. Okay, so I've set the luminance layer, and according to my notes, that's how I did it before. Okay, next up is the H-alpha layer. And so let's double click on the H-alpha, get it over here, frame it up. H-alpha, a couple things. Now the color will be Balmer. This is a color that I created. not willy-nilly. I looked up, so, okay, H alpha is a narrowband filter around the H alpha emission line, which is in the red. And, but it's not by itself. There's H beta, H gamma, H delta, and these are green and blue and violet lines. And so I looked up the colors for each of them and found an old paper by Osterbrock back in the 60s, showing the relative strengths for regions of this temperature, and combined the colors with those weights and came up with this pinkish Balmer color. And it works really well, as you're about to see. So I'm going to color it pink. I'm going to turn it on, and let me hit the default over here to tone it down just a tad. Still, it's too much. We'll adjust it. But also the blend mode. I want to change this. You see, if we layer it on too heavy, it makes everything pink, including the stars. It's adding its pinkness to the stellar colors. And we work very hard to get natural looking stellar colors. So I don't want to change those colors. So there's a blend mode called Lighten. And what that will do is it will only add, maybe I'll hit the default again, and it's about the same. It will only add the top layer if it's brighter than what's underneath it. So underneath it, we have the luminance layer with the colors beneath that. And in the luminance layer, the stars are really bright. And so if I use the lighten mode, it will keep the stellar intensities the same from below. The H alpha, it will only take data from this H alpha frame if it's brighter than what was in the luminance color frame. So let's play with this. It's too bright at the moment, and hopefully you'll see what I mean. Again, I'm going to drop this to 0 because I want all that good nebular structure. I get a little bit more detail here. And also, let's see, I'm in linear mode. Let's go to midtone. Default. Set this back to 0. Yeah, the reason it looks so weird is I was blending a midtone and a linear, different brightness and contrast for the two levels. And I have them both at midtone now, the luminance and the H alpha. And so that H alpha pink only comes in if it's brighter than what's in the luminance frame. And it's not brighter than the stars. So the stars are being drawn from the luminance color frame. They keep their natural colors, but just around them, we're adding this. So let's tune this and see what it looks like. First, let's make it not 9, 99.999. Move it like really high up, so there's no addition. This little pink area here is the Balmer that came through naturally in the R, V, and B frames. I'm going to drop this to 99.99. Nothing really, 99.9. I saw just a hint of a change here. 99. Okay, see how that added kind of pink? It extended the pink zone. We have tones of pink all throughout here. Gives it a little bit of color to the image. Let's keep going, see what happens. 98. 97. So you see it's getting kind of thick over here. And I don't want that. And I've played with different things, and often you get to the final image and you'll play around. You'll go back and adjust the luminance, H alpha, your infrared layers. And I've decided I want just a little bit. Here, that's the natural Balmer, and then here's our Balmer from the H alpha layer, colored the Balmer color. Again, see how well the color matches the natural color. It's really nice. I'm just adding a little bit. It's kind of a shame taking well over an hour of H alpha data and just using a tad, but sometimes that's what astrophotography is about not overdoing things. Okay. So that's the optical portion. It looks pretty good. Oh, and the reason I I think I just said it, but let me just be clear. If I put too much here, this region gets kind of opaque. I'm going to add on some infrared layers next, and I want this to be hazy but transparent. I want the eagle to be coming out of the mist, sort of. And so I don't want to color this too thick in here. And if I go down to 98, it's starting to get a little too thick. At least once we get the infrared layer on, you'll see that something a little more subtle works better. Okay, so that is the optical image. Now, I want to add infrared. And my favorite trick, you're going to see in many, if not most of my videos, is the Weiss spacecraft 12 micron. At 12 microns, you're pretty far into the infrared. Excuse me. And you're not really seeing stars anymore. You're seeing warm dust. And we have hot stars here. We have clouds all around it, and embedded in those clouds is dust. And so the stars are going to heat the dust, and we can see where the dust is being warmed by the stars. And it's really valuable because it gives the image a three-dimensional feel. You see what is being heated by these stars and what isn't. So let's go to the Skyview Virtual Observatory. Again, you can just type in Skyview Virtual Observatory. Here it is. Going to go to the query form. And for the coordinates M16, if it has a common name, you can just type that in. It will find the coordinates for you. And we want the Weiss 12 micron. And you can play with other layers too, but I found that the Weiss 12 micron is sufficient. Well, I'm going to add another infrared layer, but around 2 microns. Out here, farther out, the 12 is sufficient for this image. Projection, let's do rectangular. And then you have to pick the image size, and that depends on the size of your frame. So let's bring up Skynet. Telescope sites, Ceratololo. We're using the Prompt 6 telescope for these images. 15.1 arc minutes. Bring up a calculator here. Okay, 15.1 arc minutes. And so we want to bring back an image that's bigger, because we don't know if the catalog image, the archival infrared image that we're about to pull, is perfectly centered on our optical image. There could be a little bit of an offset, so we want to bring back a little bit more. So for safety, I'm going to boost this by 50%. And then it needs to be in degrees. So divide by 60.3775. .3775. Okay. And then in pixels, this camera is 2048. So 50%, I don't need a calculator. Would be 3072. Okay. 50% bigger than 2048. Okay, let's submit that request. And it's going to dig into its archive and reconstruct the image with that pixel scale. So the pixel scale should match the pixel scale of our image. Okay. I did select M16. Okay. So let's grab this thing. While it downloads, let's grab the other infrared frame that we're going to use after that. So you clear your survey selections, and I'm going to grab 2MASS K-band. And Weiss is good for illuminating warm dust. The 2MASS K-band is good for finding cool stars or stars that are lost in the dust. So highly dust extinguished stars. Talk more about that in a bit, but let's grab it, same coordinates, submit the request. download it. Meanwhile, we'll come back to Afterglow, open files in my workspace. That's where you can upload images. And go to my download folder. Here's one of them. The other has just a few seconds. So let's wait for it. There it is. Grab them both. Okay, uploading them into the workspace. Pretty big frames, 3K by 3K. It takes a moment. We should play elevator music during this process. Oh, there's one. The other failed. Strange. Oh, I could tell you why it failed. My workspace is full. So sometimes that will happen. We only give you so much space. But so let me clear out some previous stuff. Delete. Okay. Pretty sure the one that ends in 137. Yeah, we got that one. So let's get the other one. Try this one again. Yeah, once you become an active user, you fill your workspace up pretty quickly. We may look into larger workspaces for active users. But if a file upload fails, we need to have some better error messages. We'll get those in there. See, it worked this time. Good. Okay. Close it. So these two are the ones. We're going to open them. Okay. It's loading the 12 micron one first. You can see it's bigger. I have these linked up, by the way. So as I move them around, they go together. You can do that over here, syncing the orientations. Anyway, let's see. For this one, I like to color it using the heat map. There we go. And the orientation of this image is different. And so it kind of rotated my field for me, and that's fine. I have them synced up. And so it's defaulted to this orientation, rotated the other one. And for the K-band, cool stars, I normally color that one with the cool palette. It's kind of blue to white. Okay. So let's grab, we're going to select the stack, then these two, and we're going to group them all together. Add them in. And I'm going to slide them up above. I'm going to put the 12 micron one up there, and then I'm going to put the K-band 2 micron up above that. Okay. Let's look at the group here. It should be a mess initially because those ones that we loaded, they're not the same size and alignment, and it's all confused at the moment. So we're going to come over here to the aligner, and we're going to select those two images, and probably any one of the others will work. I'll select the B band. because that's kind of where we started. And then of these, the B will be the reference. So I'm going to align the 2 infrared frames to that B frame and crop to the largest overlap region, submit. It's running it as a job. So server side, job is done. So it should start to update the image. Bit by bit. Okay. Now, one thing to notice here, I'll turn off the K-band, cool stars. Here in the heat map, we're going to have to change the scale. It's way too bright, but also it has some bad data. These are regions that probably saturated the WISE spacecraft. And there's an algorithm we could run to fill in that part with kind of the bright color, but it's still not going to look right. It's missing data, and the only way to really deal with it is to crop that part out of the image. So when we're done, we're going to crop off this stripe here on the left-hand side, which will be the top of the image after we rotate it. Okay. Let's load up the infrared. Here we got the composite. We got the infrared. I'm going to split right on the composite, on the infrared. And let's zoom to fit. Okay. Back to display settings. Now I'm going to click on the infrared. And it's in linear, so let's go to midtone. That will help a lot. Hit default. And again, since this is a nebular region, I like dropping the background down to 0, keeping that consistent whenever I can. And then we're going to adjust the midtone level. Let's go way high first, 99.999. 99.999. Okay. That tunes it way down. And so that's kind of our original image. Take out a 9. So we're bringing in this kind of blown out region. That's 99.9. Getting just a hint of it here. Let's go down to 99. It's maybe too much. 99.5. Let's try that. Yeah, that's pretty good. Now these, yeah, that's pretty good. I may feel like I'm, lathering this on kind of thick here, but I don't know. Let's make a little bit more space and take a look at it. Let me get rid of these. So, remember this part's going to be gone. So all this bright stuff and the dark stuff, it's going to be gone. We'll have a little bit of the bright left over here. But I really want to show where the dust is being warmed. Like here, you can see the inside of the cloud is being warmed. Or here, this pillar pointed towards the hot stars. It's being warmed, but the undersides are not. And this gives it 3-dimensionality. So I really want to have that there in a substantive kind of way. I don't want it to be too faint. 99.9. Yeah, it's just not worth it. 99.5. And you can fiddle with it more, 99.4, 99.6 to your own pleasure. And the other thing I was going for, I want this to look like a haze, like the eagle is coming out of the haze here. So I don't want it too thick, either in the H alpha or in the 12 micron. And I still want to leave this kind of dark band here. That's going to be a visually striking thing in the image where the hot stars are. Okay, almost there. Let's, oh, and I should say for this, it's currently set to screen blend mode. If I try lighten, see, it changes the colors, and it has to do with the color palette, the heat color palette. Some colors, lighten will take stuff from this frame if it's brighter than stuff from the underlying frame. And in some colors it is, in some colors it isn't. And so it changes the colors, and maybe you like those colors, but I don't. So I decided to leave this one in the screen mode, even though technically lighten would be better in terms of preserving stellar colors. Okay, last bit, these blue stars, and that's way too much. I just want a sprinkling of these blue stars. They're showing you there's more to the story. Embedded in the cloud, in unexpected places, you have stars hidden in dust. And here, the 2 micron band, 2.15 micron KS band of 2MASS. The 2MASS telescope is actually right next door to Prompt. It's like 10, 20 feet away from Prompt Dome, from Prompt 6, actually. So these are meant to go together, but not that much. So let's tune it down. I'm going to double click on this and move it over here. And I am going to use the lighten blend mode on this. Not supposed to do that, but let's adjust the 2MASS. First, let's get into midtone and default. Why is the color that color? Blend mode. Oh, I hit luminosity, lighten. There we go. Okay. So, it will take this frame, it's on top, it takes stuff from this frame if it's brighter than from the under frame. So it's just going to take the stars. And the regions below it, it will use the original image. But again, that's way too much. Now with this one, I'm not trying to show nebulosity. I'm just trying to get a few little points. So I'm not going to lower the background. I'm going to raise the background rate. Let me highlight this region here. Right to kind of the peak or just below it. I think my notes say I used 30 last time. So let's go up to 30 and see what that looks like. Yeah, somewhere around there. So I just colored 30% of the pixels here black. And that's okay because I'm not trying to get, there's no nebulosity here in the bottom of the image. And so we don't need to worry about it. And because the lighten mode, this stuff's not going to come through anyway. So I'm just trying to get the stars. So background set there. And we want to bring this up. It's way too many stars. 99. Let's try that. Maybe 99.9. That I think is good. It's what I used before. Just hints of it. Just a sprinkling. It's just a little taste. I come back here and try like 99.5. It's a little too busy for me. And the blue stars, I don't want them to overpower the visible light stars. And blue, they're not really blue. They're in the infrared. We're just using a blue palette to bring them out. So I want 99.9. Okay. Let's grab this image. I mean, this is it. This is our final image, though we will have to crop it because of this problem here. So I'm going to export it. And I don't like this orientation. I'm going to put the eagle below. And I kind of like it moving up the other way. In most pictures, it's the other way. So we're going to flip it, like that. And then you're going to crop it. Probably something like that. And we'll save it. Now, this is pretty much your final image, but we have one final step. Save that. Stick it in the downloads directory right now. Okay, so comparing this to the original, I think I pretty much did it exactly the same, but there's one last bit here. Yeah, the last thing you want to check are your bright stars and see if you have any saturation, and we do. These two stars here show some saturation. The others, not really so much. And there's really no great way to get rid of that. You can do shorter exposures. And actually, I went back and collected a bunch of data with much shorter exposures, and the image did not look as good. With each readout, you have extra noise, read noise, and either it was dominating or the weather conditions were different. And so I went back to the data that the students collected. And my approach is just to edit it. Use whatever software tool that you want. I'm old school, so I'm going to open up Microsoft Paint. Oh, yeah. And, zoom into the region. Keep it centered, keep zooming in. I think we're almost to the maximum. There we go. And then I just edit by hand. Use this to pick a nearby color, and then use the pencil tool to color it in. And another one, color it in, maybe those two, and so forth and so on. And you can clean up these regions. You don't have to do a great job, because once you zoom out again, it's very, very small. So you need to save that. Once you clean that up nicely, you have something that looks like this. And if I zoom in, you can see, I took those out. And that's it. That's your final image. And I really like it. Physically, there's a lot going on. You have your hot blue stars. They're heating this gas. The gas is expanding up against the cloud in all directions. You have some dense regions, and the expanding gas pushes around them, creating these pillars, creating a spire. The hot gas will then squeeze these pillars from the side, eventually causing the cloud to collapse and form new stars. It's an ongoing process. And might be some of what we're looking at here. You have these kind of circular regions. Maybe those are stars that formed out of the compressing gas. Maybe not. It's hard to tell. You have regions down here. Our little blue stars are sprinkles, are confetti. This looks like a sugary confection, like some kid's birthday party. Sprinkles or confetti. These are the cool stars embedded in the dust, in the gas, stars that you can't see because of all that dust and gas. But sometimes, like here and here and here, this is probably too close together, they're actually warming the dust around it. And so you have these little glows there and there. You have these Bach globules. These were probably pillars at one point, but the pillars have been squeezed down to nothing. The hot gas is compressing around them from all directions. And so this will be squeezed down and form a star system like our own, or perhaps multiple. Anyway, that's it. I hope you enjoyed it, and good luck if you make your own eagle. Combine optical, but don't forget the infrared. There's a lot to the story here that comes out in the infrared, the three-dimensionality in particular. Anyway, good luck.